Alright, welcome back. We're looking at Math 1910 here. We're in Chapter 4. We're going to be going through Section 3 today. We're going to be talking about Riemann sums and definite integrals, how they relate. Okay, just another way of us being able to solve the area problem in calculus. Okay, so we're going to hopefully understand the definition of a Riemann sum and then how we can use and evaluate definite integrals. Okay, those are going to have limits of integration. Alright, so let's work through an example here. We want to find the area under this curve. Alright, it's bounded by the equation of f of x equals the square root of x. And we're also bounded by the x-axis, and we're bounded from x equals 0 to x equals 1. So our x values lie between 0 and 1. So what we're going to do is we're going to evaluate the limit as n approaches infinity of the sum from I equals 1 to n of f of ci times delta xi. Okay, we're going to use right endpoints of this partition. Alright, and our ci is going to be I squared over n squared. And delta x is going to be our width of our interval. See, the problem here is if we take a look at the width of our interval, they're not all going to be the same. Alright, so we got to make sure that we work through this. This is where Riemann sum is going to help us out. So if we take a look at width of the ith interval, alright, remember we have I squared over n squared minus I minus 1's quantity squared divided by n squared. So we can see where those values come from. Okay, if we take a look here on the graph. Alright, and then we're going to move forward here and break this down. So they're both over a common denominator of n squared. So we're going to FOIL out the I minus 1 quantity squared. And then we're going to combine like terms. So the width of our Riemann sum here is going to go down to 2i minus 1 divided by n squared. So we're going to replace the delta xi with 2i minus 1 divided by n squared. Okay, I'm going to step back aside. Okay, we found delta x, that's the width, and now we have to substitute our ci into the square root of x. Okay, so that's I squared over n squared. It's going to go into the square root. Alright, and then we're going to take the limit as n approaches infinity. So this is the width that we went through. So when we substitute everything in, alright, we substitute in the I squared divided by n squared for the ci, and it went into our function. Our function is the square root of x. So we replaced x with I squared over n squared, and then we just calculated our delta xi, which is the width of the interval, each interval. That ended up being 2i minus 1, okay, divided by n squared. Now, for us to move forward, alright, we've got to do some simplification through here. So, in order to do this, okay, it's convenient that the square root has I squared and n squared. So, the square root of a square, remember, is just the stuff under the square root. So, the square root of I squared over n squared becomes just I over n. We can distribute that I over n to what's in parentheses, alright? So there's going to be an I that distributes to the numerator, and there's an n that's going to distribute to the denominator, okay? So you'll end up with 2i cubed, okay? 2i squared. 2i squared minus I divided by n cubed. We're going to factor out the n cubed out of the denominator. So we can rewrite this as the limit as n approaches infinity of 1 over n cubed times the sum from I equals 1 to n of 2i squared minus 1. Okay, we have to get everything in terms of n's now. So if you remember from last section when we looked at theorem 4.2, we had to replace i's, I squareds, I cubed, and all those different factors. So make sure that you do have theorem 4.2 handy for this. Okay, we're going to rewrite that. So that's where all the n times n plus 1 times n 2n plus 1 over 6 minus n times n plus 1 over 2 came from. That's theorem 4.2. That's out of section 4.2. And you guys should remember that. We did a lot of work with that. So now that everything's in terms of n, right, we did that so that we could get rid of the summation symbol. Now we want to be able to take the limit as n approaches infinity. Okay, that's really going to be key for us to do some simplification. Alright, so the numerator we got to do the binomial multiplication, distribute the n through. You guys should be able to do that algebra. So the most simplified form for us is 4n cubed plus 3n squared minus n, all divided by 6n cubed. All right, we're going to take the limit as n approaches infinity. So if you remember how we do that, remember there's 3 scenarios. All right, the numerator's exponent is greater than the denominator's. The numerator's exponent is the same as the denominators, which we have here. Remember that told us that would be the leading coefficients, okay, when we did this. Or there was the other scenario where the denominator's exponent was greater than the numerator. But for us, this works out well because we have n cubed over n cubed. So that tells us it doesn't matter what anything else is, the answer is the leading coefficients. So it's 4 over 6, which reduces down to 2/3. Okay, so we learned that in chapter 3 when we were doing limits as n approached infinity. All right, but that one's got to stick with you. We're going to use this, multiple times in the chapter. All right, so we're able to define here how this works out to the area ends up being 1/3 there, okay, on this piece. Okay. So moving forward here, I'm sorry, I didn't need to say, for this particular region, okay, I'm going to step back here because that was probably a little slightly confusing. Okay, so what we came out with, we have the limit as 2/3. Okay, so if we look at the limit here on this region from 0 to 1 of x equals y squared, that's the same thing as saying y equals the square root of x. Okay, so we can say in this case, right, we ended up being this one right here, all right, ended up being 1/3. But this one, okay, because we have different boundaries, okay, it ends up being 2/3. So if we do different widths, okay, so that's a difference for us in the different airs there. Okay, so what do we really just kind of do? We did what we call a Riemann sum. Okay, so for us, we're going to let f be defined on a closed interval from a to b, and we're going to have a delta x be the partition of a to b, right? So when we work through all this piece, it's really just that sum that we just did, I equals 1 to n of f of ci times delta x. We call this a Riemann sum of f because we're taking partitions of delta, okay, as we go through this. And we did all this, in 4-2 and things like that. When we talked about, left hand and right hand sums and things like this, there's more forms of Riemann sums, to come when we do this. But this should be the one that we're going to use here in this section as we go through it. All right, so when we define the Riemann sums, we have to find the width of the largest subinterval, okay, on that partition of delta, because remember, they're not going to all be the same. So when we do this, we have what we call the norm. The norm, right, see the two parallel lines with the delta in between? That signifies the norm, okay? So if every subinterval is of equal width, the partition is a regular, and the norm is denoted by delta x is b minus a over n. That's if it's a regular partition and everything is equal, right? The first examples we did in chapter 2 where we had 2/5 and 2/5 and 2/5 and 2/5. So if we do a regular partition, our norm is b minus a over n. Those are what we've been doing all along. Okay? Now, if we do a general way of doing this, a general partition, so maybe they're not all the same. We have b minus a over the norm is less than or equal to n. Okay, so if we have a general partition, we'll use that one. So if we take a look at the number of subintervals, okay, as it approaches infinity, the norm of the partition equals 0, okay? So if you look at that, as we approach infinity, the norm is going to go to 0, all right, because that denominator is going to get really big, right? B minus a over n, as n is going to infinity, the denominator gets big, right? So that means that the norm is going to go to 0. However, the converse of it's not true. Okay, if we have the participant on 0 to 1, okay, it can be given like this. It actually ends up going to 1. in that scenario. Okay, so just remember, gotta be careful and pay attention to, it doesn't always imply that it's always going to go to 0. Okay, it's going to depend on the equation and a few different things that we look at as we go through them. All right, but next there's a little bit easier way, and we're going to step into definite integrals, and then next section is going to get even easier because we're going to talk about the fundamental theorem of calculus. But for now, let's talk about what a definite integral is. Okay, so in section 1 in this chapter, we talked about indefinite integrals, right? We didn't have limits of integration, and we had a general solution where we had to integrate and have a plus c, or if we had initial conditions, then we would be able to find the particular solution. All right, so this helps us get more of a particular solution when we have definite integrals here. Okay, so just to read through the definition, if f is defined on the closed interval from a to b and the limit of the Riemann sum over the partition delta, okay, we get the limit as the norm goes to 0 of I equals 1 to n of f of ci times delta xi. It exists, then f is said to be integrable. All right, so we can actually take the integral on a to b. So our whole limit actually equals a definite integral. The integral from a to b. Notice those are what we call the limits of integration. We have an upper limit, which is b, and a lower limit, which is a. It's always going to be, left to right in that scenario, of f of x dx. So there's where we're kind of stepping in. We're taking our Riemann sum and we're turning it into a limit, okay? And then as our norm approaches 0, right? Because before we had as n approached infinity. Well, if n approached infinity, that meant the norm went to 0. So that's why we can rewrite it this way. Okay, so we're going to rewrite it as what we call a definite integral. So we're going to have the integrand, we're going to have an upper limit, a lower limit, a function, okay, and then the variable of integration. So we're doing kind of what we did in section 1, but now we're doing it with limits, which helps us find a particular solution every single time when we have a definite integral. Definite meaning it's a defined solution. Remember, indefinite meant we had to do plus c because there was multiple solutions for this. All right, so an important theorem 4.4, right? Continuity implies integrability, okay? Just like it implied differentiation, same thing applies that we're able to take the integral of it. So if a function f is continuous on the closed interval a to b, then f is integrable on a to b. That means the definite integral from a to b of f of x dx does exist. Okay, just like it helped define and allowed us to take the derivative of functions as well. All right, so let's do an example here. We want to evaluate a definite integral. All right, so we have an integral here from -2 to 1 of 2x dx. Okay, so how are we going to do this? Well, for now, we're going to use our Riemann sum and substitute in. Okay, so we know that it's continuous on that, so since we know that it's continuous, we know that we can actually integrate it. Okay, so very important there. All right, and we're able to take that limit as the norm approaches 0. So for us to be able to do this, we're going to have b minus a. Well, how do we get b minus a? I'm going to step back a slide. Those are our limits, okay? Those are our limits. B is 1, a is -2. All right, so we have 1 minus a -2, which gives us 3. Okay, so b and a are our limits of integration, and you do keep the signs with them. All right, so our delta x becomes our limits of integration, so b minus a over n. So we're going to get 3 over n for the delta x piece. Okay, then we have to calculate our CI, and general rule of thumb, right? Use the right endpoints because they're easier. So when we calculate our CI, make sure you got this written down, okay? It's going to be a plus I delta x. Okay, so -2, that's our a. Okay, that's our lower limit of integration, plus our I delta x, okay, which is 3i over n, right? We're going to take I, and our delta x we calculated for our interval, right? That's our 3 over n that we calculated at the top. So our CI that we're going to substitute into the original equation is negative 2 plus 3i over n. Okay, and then we're going to take the limit as the norm approaches 0. Okay, so now we're ready to substitute everything in. So we can say the integral from negative 2 to 1 of 2x dx is going to equal the limit as the norm approaches 0 of I equals 1 to n of f of ci times delta xi. And we just calculated what ci is going to be, and we calculated what delta x was going to be. Okay, so we're able to substitute those in. Okay, and because we know that the limit as the norm goes to 0 is the same thing as saying the limit as n approaches infinity, okay, we have to revert back to using n because we have i's, right? And we're going to take those i's and use theorem 4.2 and put them all into n's so that we can eliminate the summation signal. Okay, so if we take a look at this, we have the limit as n approaches infinity of I equals 1 to n of 2. Okay, remember this is our function. Our function is 2x. So we have 2 times we replace x with our ci, which is negative 2 plus 3i over n. And then we replace delta x with 3 over n. So now we've got to get all of this stuff in terms of n. So there's really only one I term here we got to worry about and be able to rewrite. Alright, so we'll distribute through, we'll factor some things out, and separate it. So once we do that, we're going to have the limit as n approaches infinity of 6 over n times I equals 1 to n of negative 2 plus 3i over n. Now we have to replace the I with its n equivalency, which is from 4.2, or theorem 4.2. Okay, that was in chapter 2. So as we break apart our summations, okay, we can substitute in our n values. So when we replace the sigmas with its n equivalency, okay, we end up with the limit as n approaches infinity of 6 over n times negative 2n plus 3 over n times the quantity of n times n plus 1 divided by 2. Okay, so if you're not seeing that, let me know if you need to zoom in or things like that as we go through this, okay? But it's important that you remember what we did in chapter 2 where we're rewriting those summations in terms of n. Don't neglect the one that's just a constant, okay? You need to make sure that you do that. Alright, so when we simplify all that down, right, and combine like terms, we end up with the limit as n approaches infinity of negative 12 plus 9 plus 9 over n. Well, we know now when we take the limit of this function, we're going to get negative 12 plus 9 plus 0, right? The limit as n approaches infinity of 9 over infinity, right, goes to 0. So that piece goes away when we do this. Okay, so our final answer is going to be negative 3. Okay? So lots to work through. So where does that come up with? Okay, so if we take a look at the graph of this function, all right? So the graph of this function is showing from x equals what? Negative 2 to x equals 1 of f of x equals 2x. So if we graph this function, right, limits the x-axis, and the limit is also negative 2 and 1, which should make sense, right? Because if we take a look, the area from the x-axis to the curve on the left-hand side is greater than the area from the x-axis, you know, to the line on the right-hand side. So since the area on the left-hand side is negative, okay, it's going to dominate. So it makes sense that our answer is negative. Okay. However, it doesn't represent the area of the region shown correctly, because when we do a definite integral, they can be positive, negative, or 0. However, we want to find the area. These areas don't really cancel each other out. Okay, we have to make sure that it's continuous, not negative, okay, as we go through this. The problem is when you get a negative definite integral, it's not accurately representing the area, though. We don't have negative 3 area. Okay, so just make sure that you understand that piece. But that's the solution to that, but that doesn't mean that it's correctly depicting what the area is. Okay, It's just telling us that the negative portion is dominating the positive portion. Okay, but it's area, so they both should be positive. All right, let's take a look at theorem 4.5 here. If f is continuous and non-negative on the closed interval a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is defined as, okay, a to b of f of x dx. So we're going to integrate that. We're going to use this as a definite integral, and we're defining the area under the curve, okay, using the integrand. Alright, so if we have an example of theorem 4.5, I can take this graph of the function f of x equals 4x minus x squared and bound it by the x-axis, okay, as depicted here. And my limits of integration, my left hand, which is my lower limit, okay, is 0. My upper limit is x equals 4, okay, so I can integrate from 0 to 4 of 4x minus x squared dx. Okay, so that's our definite integral there for this function. So we can, go through what we've been doing, or we can, I'm going to step back for a second, we can go through what we've been doing. Alright, same thing that we just did, use the limit as the norm approaches 0 of f of ci times, delta xi. You can do that same piece there that goes through it, and you have to come up with everything, right? So you're going to have 4 minus 0 over n, okay, so for your xi piece, your delta xi, okay, and then you're going to rewrite your other pieces. You got to come up with your ci using your the limits as we talked about before. So the right endpoints, because they're the easy one. Okay, so fill it in, go back to the last example, and you would set it up the same way. Okay, so let's just talk about how do we sketch this graph, because sometimes we can just use geometric shapes. Okay, so example 3 is going to go through geometric shapes that are defined by the integral. If we have a nice perfect shape, we know how to calculate the area of a square. We know how to calculate the area of a rectangle. We know how to calculate the area of a triangle, or different things like that. We know how to calculate the area of a trapezoid, or a semicircle, or a circle. So there's distinct shapes that you know how to calculate the area of, and you've been doing, most of your math career. So if we actually sketch out the integral, you're going to see how it defines specific shapes. So we're going to go through these examples here, A, B, and C, and we're going to define and actually draw the shape that they create. All right, and then we can find the area that way. So if we take a look at this first integral here, we're going to integrate from 1 to 3 of 4 dx. So if we graph that, notice the line, it's just 4, so it's always going to be 4. So we can draw a line at y equals 4, and our limits are from 1 to 3 on the x-axis. So we can see that that's going to create a rectangle that is 2 wide, right? From 1 to 3 is a space of 2. It's 2 wide and 4 high. So we can say 4 times 2 is 8, right? Length times width, base times height, however you want to see it. All right, so we can use calculus and apply some old school geometry and mix it in. So this integral from 1 to 3 of 4 dx is going to be an area of 8. All right, if we take a look at the next shape, okay, we were given the integral from 0 to 3 of x plus 2 dx. If we graph x plus 2, right, the y-intercept is 2, and then it goes up, just like the graph of x would. So it's sketched right here. And if we, use the limits from 0 to 3, we're going to create the trapezoid. All right, so remember the formula for the area of the trapezoid is base 1 plus base 2, okay, times the height times 1/2, or 1/2 base 1 base plus base 2 times height. So if you turn your head, sideways to the left and you look at this, our first base is from 0 to 2 on the y-axis. Our second base is from 0 to 5 on the y-axis. Okay? And then we know the width is from 0 to 3. Okay, so if we were to draw this out, you could see the trapezoid, and it's just a geometric shape, so we know that it's 1/2 times 3 times 2 plus 5, and we end up with 21 over 2. Okay, let's take a look at the last example here. Okay, it's a semicircle, and we know we have the limits from -2 to 2 of the square root of 4 minus x squared. So we know that it creates a semicircle, and we can see that the radius of this circle goes from what? 0 to 2, so the radius is 2. And it's a semicircle, so we know the area of the circle is pi r squared, and since it's a semicircle, it's half a circle, we have to do 1/2 pi r squared, where r is our radius. Okay, so we're going to take 1/2 times pi times 2 squared, and we end up getting a 2 pi. Okay, so that's the area of this particular graph from -2 to 2. Alright, so just going through some common sense pieces here. If we have the definition of a definite integral of f on this interval a to b, we're really saying that a is less than b because a is our lower limit, b is our upper limit. Okay, sometimes we can extend it and cover cases when a equals b or a is greater than b. So we're going to have a couple properties that we're going to talk about in a little bit. Okay, so it makes sense, right, if we talk about the area of a region being 0, if its height is 0 and its width is 0 as we go through this. But we have these two special properties that help define some definite integrals. So if f is defined at x equals a, then a to a, notice the limits are the same, a to a of f of x dx. Anytime the limits are the same, we will always get 0, right? Because there's no height, no width. Okay, so that's what we were just talking about on the previous slide. Okay, so it's a special definite integral. Then, okay, number 2 is important as well. If f is integrable on the closed interval from a to b, then b to a of f of x dx becomes negative a to b of f of x dx. Notice if we flip the limits of integration, we can change the sign and make it the opposite. Okay, so 2 important definitions of some special integral cases here. So we'll go through a couple of examples with them. So if we take a look, and we're going to evaluate each one of these definite integrals. So if we look at the first one, okay, we have the integral from pi to pi of sine of x dx. You don't need to do any work here. It's from pi to pi, so the limits are the same. Anytime the limits are the same, it doesn't matter what the function is, sine, cosine, tangent, it's a polynomial. If those two limits are the same, the answer is automatically 0. Okay, and if we look at the next one, okay, 3 to 0 is going to produce a bad value for us potentially, so we want to make sure that we go lower limit to upper limit. So I can rewrite this integral. We have the original integral is 3 to 0 of x plus 2 dx. Okay, well, if we want to change the limits from 0 to 3, we can do that and swap the limits as long as we put a negative in front, because it has to be the opposite because we flipped the limits of integration. So it becomes from negative 0 to 3 of x plus 2 dx. Alright, so that it works out when we do this. Okay, so that's applying the 2 properties. Alright, next is the additive interval property. Okay, it's theorem 4.6. It states if f is integrable on the 3 closed intervals determined by a, b, and c, then we can rewrite this. Okay, so if we have the integral from a to b of f of x dx, if it equals the integral from a to c of f of x dx plus c to b of f of x dx. Okay, so we can rewrite that, because some pieces will cancel out when you go through this. It's very important for us to do one like this, the absolute value function. So remember, if you graph this one, it's a v. So we need to break it up because the slope on one side is negative, the slope on the other side is positive. Alright, and our limits didn't agree, so we remember the derivative at that specific point doesn't exist. So we got to break this one up to actually get the area under the curve for this. We're going to use the additive interval property. So since we have the absolute value of x, we're going to have to know, right? Because even though the graph, is somewhat continuous to separate that one point, the vertex of it, we have to know that the slope on the left-hand side is always going to be negative, and the slope on the right-hand side will be positive for this particular, function, the absolute value of x. So if we break this up and we say from -1 to 0, we're going to get negative x, right? Because the left-hand side of that v is continuously going down or decreasing. Plus, if we go from 0 to 1 and look at the graph of the absolute value function, we get just x. Okay, so it's very important that we understand how to break this up. And you'll always use this additive interval property anytime that you are doing an absolute value problem. Okay, so anytime you have an absolute value problem, you're going to want to approach it this way, because you got to make sure that you accurately depict, the negative slope on one side of the vertex and the positive slope on the other side. Okay, and I'm not going to go through those integrals. You should be able to do that when we do that. Or if you did the triangle, right, you could just graph the v. You have your two triangles, and you know the height, the width of each one, since 1/2 base times height. Okay. So if we take this, we have 1/2 plus 1/2, so the total area ends up being 1. Okay, so very important there. Alright, let's look at theorem 4.7. We have properties of definite integrals. Alright, so if f and g are integrable on a to b, and k is a constant, then the functions kf and f plus or minus g are integrable on a to b. Okay, so we're just being able to define this, that for us to do this definite integral, and we have some sort of constant times the function, I can factor out that constant, okay, and then take the derivative. Okay, if I have a sum or a difference scenario, like in 2, I can write that as two different integrals. So I could say that I have the integral from a to b of f of x plus the integral from a to b of g of x. So it's very important that we can break it into its different composite function pieces there. Okay, and that helps us, as we analyze certain things. So we're going to use 3 given solutions here. So we're going to evaluate this integral from 1 to 3 of the polynomial negative x squared plus 4x minus 3 dx. So we're going to use the following values. If we have the integral from 1 to 3 of x squared dx, that value is 26/3. If we have the integral from 1 to 3 of x dx, that would be 4. And if we have the integral from 1 to 3 of dx is 2. It's giving us defined values. We're going to use those 3, okay, and apply them, right? We have a negative polynomial, so we can factor out a negative first before we do these. Or we can keep it in if we want to. Whatever works easiest for you, how you want to do that. But we can take this polynomial and set it up as 3 different integrals. The integral from 1 to 3 of negative x squared dx, plus the integral from 1 to 3 of 4x dx, plus the integral from 1 to 3 of negative 3 dx. Right, and why are we allowed to do that? We're going to step back a slide, and it's theorem 4.7, property 2. Okay, we have a sum and difference. It's really, for our polynomials as we're able to do this. Okay, and now we can substitute in the values. Notice as we broke that up, okay, we can get our different values there. Okay, so factor a negative out of the first one, okay, and then rewrite them, and then we can replace them with the correct values. We know they're given to us, right? The integral from 1 to 3 of x squared dx was 26/3, so we substitute that in. We know we have an integral of 4 times 1 to 3 of x dx. We know that that ended up being 4, so 4 times 4 for that part, minus the 3, the constant out in front of d is just dx, okay, that is given to us as 2. So we just substitute in our values and then simplify them down and combine like terms, and we end up getting 4/3. Alright, so it's very apparent, it shouldn't be too hard, but you're going to have a couple of homework problems where you've got to do this. It gives you the individual values for certain chunks of the integral. Alright, so you're going to use the sum or the difference, formulas for this, to break it into the different integrals that are going to match the values that you have, and then you replace the integrand and the dx with the given value that you are instructed for those particular intervals that you're integrating. Okay, so this one should be fairly self-explanatory. Alright guys, well that's it for this lecture. Like I said, if you have any questions, just always email me or let me know if we need a team meet or Zoom meet or anything else like this. Else guys, have a great day. I will see you in class.